Hello, welcome, and an excellent evening. Tonight we want to do some more Let's Code MS-DOS, and we're going to continue with the tricks that the EGA and VGA graphics cards have up their sleeves regarding the text mode. A couple of episodes back we already had this funky program here displaying a plasma effect in text mode and redefining characters to display varying sizes of squares, basically, to get some kind of a dithering effect. We do this by calling an interrupt. I think that's here exactly. Interrupt 10 to be precise, with subfunction 11, I think, to redefine certain characters. And this is all fine and great, but if we want to update the graphics inside of the text, we might not want to do this via an interrupt because it's relatively slow. Plus, we lose certain characters, and we want to make a graphics effect where we can draw arbitrary 3D graphics in a little window on the screen next to regular text. So I prepared a little program called TextCube, and it's mostly empty, at least in certain parts. Oh, I forgot to delete one function for you, but that doesn't matter. So we get that for free. We already know the disable cursor function and the set character width function from the last video, so check on that if you need to. We also know the file cube.c, which we used in a different video as the main program. It draws a rotating cube using fixed point arithmetics. I also not be talking about that. You can watch that video as well. Plus we have the VGA, C and header files for regular VGA stuff, some definitions of ports and similar things. What we're going to talk about today is how the EGA and VGA graphics card can actually not only use 256 characters as you have on the IBM PC. The lower 127 are just the regular alphanumeric characters. And then this extended set here is basically the stuff that IBM defined for their PC. And it has some international characters, German umlauts, Spanish and French characters, similar things, some international currency symbols, as well as block graphic symbols that we use, for example, to draw frames around text windows and similar things. And that means we have 256 characters that we can use. But we might also really want to use them, not redefine them. But on the VGA card and the EGA card, you have a second set of 256 characters that you can enable, actually. And for that, we need to talk about attribute bytes in VGA memory and EGA memory, starting at B800 hexadecimal. You have interleaved a character and an attribute byte, and another character and another attribute byte, then the third character and another attribute byte, and so on up to 80 columns in regular modes. There's also different other modes, but we're talking about regular modes. And an attribute looks something like this. The attribute byte has, of course, 8 different bits. The lower 4 bits encode the foreground color, and the next 3 bits define the background color. And then we have the 8th bit, which is blinking bit. If you turn this on, then the text will blink, actually. Okay, so we have 4 bits for the foreground, which gives us 16 colors, 3 bits for the background, which gives us 8 colors, and an 8th bit for blinking. And it would be superb if IBM had said, well, we make the 8th bit optionally to toggle between two different character sets, but they didn't. They said we take the fourth bit in the foreground color, reducing the foreground colors to 8 colors, which is a bit of a shame, I think, but that's how they did it. And with this you can switch around between the two different sets, because you only have 8 bits, of course, for the characters, and you would need 9 bits. So this is basically becoming the 9th bit to select from 512 different characters. Okay, enough said. I'm gonna delete that again. First we define a couple of constants, VGA width and height, 80 by 25, number of text colors that we have, 16. I'm not sure we even need that, but that doesn't matter. Then the location of the VGA memory buffer in text mode, which is segment B800 and offset 0. And the regular graphics memory buffer, which is A000 and offset 0. But it's also where we can access and manipulate the character data if we want to do this directly. And the 0th offset here is actually the current character set that you are looking at. And then the EGA card has multiple character sets. So 0xB800 000 is the first character set, let's call it that, not font. And then you can have 4 more for the EGA card, 4000, 8000, 8, 9, A, B, and then it's C, C1000. These are the next ones. Let's say here second character set, third and fourth. And let's keep this here as a reminder so you can look it up. And that's all very fine. And you can actually set via this interrupt down here. We'll talk about that in a minute. Which character set you're actually using for the first character map, and the second character map. So you're completely free. You can pick any 2 of the 4 that are available. The VGA card has even more. It has even double amount. So on the VGA card, VGA only, you also have 2000, which is the 5th. And then you have 6000, which is the 6th character set, and so on. You can probably already guess what it's gonna look like. 8000 is the 7th, and then you have E1000, which is the 8th character set. But we're not going to use that because it's also tricky how they hid the 3rd bit to select the map inside of the register. So we'll keep using only only these 3 character sets. The first character set will just be our working set that we're printing characters with, and the second and third will be the front and the back buffer for double buffering, and we'll swap them around. So that's why we have a so-called front page, which is in the beginning 4000, and a back page, which is 8000. And then we're going to swap that and display only one. For that, we have a swap macro. I'm not going to talk about that. You can Google that. It's a nice trick that you can do in C, but yeah, that's fine for the moment. Then we'll print out a little frame buffer on the screen made from 32 by 8, not exactly, 24. That's actually not correct. 24 by 10 equals 240 characters. We will have 16 characters left over that we're not using. You can also do something like 16 by 16 for a whole 256, but I think 24 by 10 has a nice aspect ratio. It's almost square. Let's type it here. It's almost square. And that's what we're going to print out. You can think of this in the following way. You have basically A, B, C, D, E, F, G, and so on. Let's go to VW and X, that's 24 characters, and then Y, Z, and I don't know, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. And the same goes up here. We're not starting at A, but at the character 0 all the way on the other page. That would have been here if we had the complete ASCII table here. But basically from the bottom left to the top right, we're incrementing the characters one by one. And that is our frame buffer, because then we have every single character from the second set on the screen in our little window, and we can manipulate each pixel inside of each character cell to draw arbitrary graphics. Many of them will be empty most of the time with the rotating cube, but some will have some line parts running through it. So that will look quite nicely. And each character is 8 bits wide, 8 pixels. The 9th character on the VGA card that we disable is just repeated. And the character height, the maximum height is 32 lines. So each character is at most 32 bytes, but we're using only 16 lines from that, because the standard height in this mode here in 80 by 25 is 16 characters. So the full buffer is 8 kilobytes times 2 bytes for 2 pages of video. And we are having the pointer here, the character table, which I think we don't need because we already have the character buffer here. So I think this is redundant. I might want to delete that and just use character buffer. Okay, let's give across these two functions because we already talked about them. The thing is, we can't access the graphics memory at 0xA00 from the get-go in text mode. It's not accessible. And to explain a little bit more, the graphics memory of the EGA and VGA card outside of the chunky modes is actually using bit planes. We have 4 bit planes on the EGA and VGA hardware. And we have in text mode, bit plane 0 is the characters. So 8 bits in a row give us 1 character. Bit plane 1 is the attributes. 8 bits in a row give us 1 attribute byte. And bit plane 2 is the character data. So, and bit plane 3 is not used. So what you actually want to have is access, write access, and maybe read access to bit plane 2 to manipulate the data in there. When you access 0xA000 memory layout, when you access this, you want to be accessing bit plane 2, and by default you would be, first of all, you can't access anything in text mode at this position, but if you switch it so that you can access A000, of course you first maybe access bit plane 0 or whatever the mode register says. So we first need to open the access to bit plane 2, and for that we need the sequence controller, and it has a couple of registers that we need to write, 4 in total. Let's do it like this. The first is the reset register. Let's see, we're here at the, exactly, this is the sequencer registers. The reset register is index 00, and we will have to do a asynchronous reset. So we're setting this register to 01. And the way this works is we first write the register number as the low byte, which is 00, and then the value that we want to write, which is 01. And we can put that in a word. And I'm gonna put here 00 reset the and we're writing 0x1, reset the sequencer, something like that. That's exactly correct, and we're gonna do the following. I'm gonna already write this out for you because there will be a couple of other values that we need to write. We will disable all the interrupts so that no interrupt can mess up our VGA setup, and then we will enable them again, very important, otherwise keyboard will stop working. And we will iterate over all the values, and we will put 4 values in there because we need to write to 4 registers. And we will simply write a word to the sequence controller index register, and a 16-bit write will also write to the next port. So sequence controller index +1, which is sequence controller data. And it will write both bytes in one go. Registers index I. So that's very nice. And we will also have the graphics controller, we will look at that in a second, which also controls the layout of the memory of the VGA card, and especially selects the bit planes, for example, that we want to write. And there will be 3 registers that we need to write, and it will be the graphics controller index, and very similar, but with the other registers. So what else do we need to set up? Next register that we need to write to is the map mask register, which is the memory plane write enable. And this is memory plane 0, 1, 2, and 3. So what we want to write to is enable bit plane 2, right? Which would mean that this is value 1, 2, and 4. So we want to write a 4 into register number 2. So let's write that down. Map, what is it called? Map mask register. And 0x4 means write to bit plane 2 only. Every bit that you set will be enabled for writing, and this way we only write to bit plane 2, which is exactly what we want. Next up, memory mode. Memory mode. It's down here. The memory mode register can enable the extended memory so that you can access the whole 256K of the EGA and VGA cards. Otherwise it will behave like a CGA card or MDA card and only give up to 64 kilobytes. And the odd-even chaining for the character attribute interleave is also there, and the chain for the VGA 256 color modes, which we don't need. But here we want to set everything to 0x7, which is enabling the odd-even disable, so disabling odd-even mode, enabling the extended memory. And this one here is not documented, but also important, but I haven't got my book here to tell you what it is, so you can look that up somewhere else. The register was 4 that we write to, so 0x4 is the memory mode register. 0x7 means odd-even disable, extended memory, basically. That's the important stuff that we need. And then the last thing is to get the card out of reset, and that's done by writing a 3 into it, disable reset. And we're gonna take away the extra comma, which shouldn't hurt, but it hurts if I press return. Let's take a look. I think this is, exactly. Actually we did a synchronous reset because this is active low, which is why when we put a 3 in there we get no reset, and if you put a 0 in either of the bits you get a synchronous or asynchronous reset. Not sure what the difference is, but to prevent the loss of data, bit 1 must be set to 0 during the active display interval before changing the clock selection. Okay, Never mind. The graphics controller also has stuff going on. And no, this is not what I wanted to see. Let me fetch the documentation for that. So here is the graphics controller registers. First of all, we need the read map select register, which is the counterpart to the sequencer controllers. No idea why they put it there. This value of this field is used in read mode 0 to specify the display memory plane to transfer data from. Yeah, interesting. I don't know why they designed it that way, but that's what IBM did. So this is register 04, and we want to have bit plane 2. So here, because it's condensed to actual 2-bit values, and you can't enable multiple bit planes. And it also says here, due to the arrangement of video memory, this field must be modified 4 times to read 1 or more pixel values in the planar video modes. Terrible. So we have to write a 2 to it, and we can only read from 1 bit plane. So that's actually pretty inefficient in this mode. But you can read multiple pixels at once, but only 1 bit at a time. So you always have to think about that when programming in planar modes. So this is the read mode, read map select register, which is 0x4. Select bit plane 2. That's that. The next thing that we want to do is setting the mode register, the graphics mode register, which is 5. And here we, I think, have to clear everything when set to 0. 256 color shift mode, we don't need that. Okay, everything has to be set to 0. It's also the exactly the odd even mode. When set to 1, this bit selects the odd even addressing mode, and we have to disable that. So 0005. This is the mode register, and most importantly, disable odd even addressing. Last value here is the miscellaneous register right below here. It has the memory map select in there, and we want to be able to access the A000 plane, and I think we could either write a 00 or a 01, but the documentation I got said to just enable the whole 128K region. So let's do that by writing a 0 in there as well. And also it's another control bit for the odd even. There's like 3 different bits that enable the odd even addressing, which is so weird, but it is like it is. And yeah, that should be fine. And the alphanumeric mode disable. But we're not in in graphics mode. When set to 1, this bit selects the graphics mode, so we keep this at 0. Once more, 0x6 is the miscellaneous register. Disable odd even, enable 0xa segment, I would say. Okay, this is for opening access to the fonts. Furthermore, we have to do the reverse after we're done with our shenanigans. Otherwise, people can't use the text mode properly. So we're gonna do the reverse basically, and I'm gonna go a bit quicker through this, hopefully, because we still have a lot of stuff to cover. First of all, we are gonna go back into reset. That's the same, and also go out of reset. That stays the same. The map mask register gets a 3, which turns on bits 0 and 1. So 3 means write to bit planes 0 and 1, which is the characters and the attributes. The memory mode is being reset to 03, and we can have a quick look. And oh, is this correct? I should have looked at 4 here. We have to enable the odd even again. So this has to be set to 0. The extended memory gets set to 1 actually, it seems, because we're writing a 3 into there. So memory mode and odd even enable, and we keep the extended memory, it seems. And then the disable reset. The graphics controller looks similar. The bit plane by default that we want to write to is the 0th bit plane, because everything is in odd even. Every other write will go to bit plane 1. The mode register goes to 1005 because the 5th register is our read map select. And let's have a look. 10 in hexadecimal is in binary 1 with 4 zeros, so we enable the host odd even and put everything else in 0, including the write mode. So this is basically enabling odd even again. And similar here, we write an E into the miscellaneous register, which means in binary we set memory map select to 11, which gives us the B800 region, which is fine, which is exactly what we want. Plus we are enabling the odd even, and this stays at 0, so we keep the text mode. So we're enabling odd even and enabling access to B800 basically. Okay, whew. Let's take a quick breath. We now know how to open up the graphics card to reveal to us the different bit planes with the character data. And we know where the character data lies, namely at the offsets that we have here for front page and back page. And that is now hopefully working. Now we need to set up our screen and be able to flip the character sets. I'm gonna disable drawing the cube right now to show you after the setup screen what we can actually do. And I'm gonna turn off this loop here for a second to make this a bit easier and to show you a special feature of graphics in text mode. So we're gonna write a setup screen routine which will draw the frame buffer, and yeah, that should be fine. We are also filling the background with a ton of characters, and that should actually already be working. But yeah, there's a typo. Let us try and run this program as it stands here. Where is our error? Undefined symbol char table. Okay, yeah. We're gonna call this char buff. Okay, so this is our backdrop. This is the whole ASCII table repeated all over. Here it starts with character 0, and then 1 and 2 are the smileys, and then all the other graphical characters, alphanumeric characters, going into the Greek symbols, other mathematical symbols, and then here the square is the last. That's the character 255. And then it repeats all over again, so that you can see you're in text mode. And every graphics character does still work, even when you're manipulating this stuff. Actually, we're already opening up the font, doing our draw loop and closing the fonts here. You can't do that inside of the loop, or you will get... In DOSBox it will work, but if you test it on a real machine, it will throw your monitor into crazy mayhem because the monitor loses sync during this opening and closing of the font. So you should do this as rarely as possible, okay? Good. That being said, we are gonna draw our frame buffer, which should be very nice. And it's a bit tedious, so bear with me. We need some coordinate variables, I call them x and y, and we need a put character function that we'll fill in first. The put character function directly writes to the VGA buffer that we defined above, which is the one at B800. And it's simple arithmetics. Every scanline is 160 bytes in width, 84 characters, 84 attributes. Plus our offset needs also be multiplied by, or x offset also needs to be multiplied by 2 because every character and attribute. Again, plus 0 for the characters, and that will be our character. And then we can copy this line and basically add this here and put the attribute byte in there. So now we have a very fast put character routine here, and that is actually great. So we can start drawing characters. I'm not going to explain this in detail, but here we are drawing to the upper left border or the top border, then the side borders, and then the bottom border. Basically, we're drawing this here first, then we're drawing this and this part here, and then the bottom border with the corners. So you can figure out the different things here. The first character that we need is a upper left box, which is this. And you can look this up in such an ASCII table here, and I put in character 201, and you can type it in by holding down the Alt key, and on the numpad, not on the regular numeric keys, but on the numpad you type 201. Should come here. And similar, you can do 202, 203, 204, and figure out all the characters if you don't have an ASCII table. You can also type something like 64, which is the @ symbol, or 65, which is the capital A. You can type in any characters that way, which is nice. And yeah, that's fine. And we also write the attribute. And then we will write a very long line across the screen. So x equals big X, x smaller than big X plus the width of the frame, plus x. And we're gonna take us the put character routine, replace this with x, and y minus 1 is correct. And then this here should be a 205, which is the horizontal line. And then we can write the right side of the box, the right corner. That should be, I didn't write that down. The right hand side is 187. 187. There you go. And running this already gives us, yeah, kind of the right thing, because I forgot to update the x coordinate. X plus width, I think. Yeah, this is looking good. Now we have a part of a box coming up. Very nice. Now we can draw the left and the right side of the border. So this time we are running over the y coordinate, y less than y plus height, plus y. This will give us two different characters that we need to put down. Put character at x minus 1 and y. And this will be the character 186, I think. Yeah, that's the vertical bars with the same attribute, of course. And then we can also put this on the right side of the box, if we do this correctly. That should be plus width and that should give us, yeah, this gives us almost the whole frame, right? So we only need to copy this whole block up here and change out a couple of characters and a couple of coordinates. Namely, this will be -1, and this should be plus height, I think, right? Yes. And here as well, we are drawing the bottom one. And of course, the box will be wrong because it has these downward facing thingies. So we need to replace them with their counterparts, and the counterparts are 200 and 205. No, that was this one, 188. So we drew a box. Now we have to fill it in with the alternate character set. Let's try that. That is actually doable with another loop. Let's go from y equals 0 while smaller than the height plus y, and then the x also x less than the width of the frame buffer plus x. And now we fill in the VGA buffer. First only the character, and then I'm gonna fill in the attribute with the fourth bit enabled. So we switch to the second character set basically. So the y coordinate is capital Y plus our current offset, again times 160 plus x times 2 plus the 0 for the characters. And this will be a small formula to get the nth character in our loop. We could also have a running variable that you always increment if you want to do that, but you can also calculate it like so. It's totally up to you. This gives us character from 0 to 240 basically at this exact location, but you can also have the run variable as you wish. So this should fill in everything like so. Yes, here's character 0, 1, 2, 3 and so on. And you already knew, for example, this is the 64th character, 65th and so on, going upwards. And here you see all the border thingies. And here you also see the problem. If we were to redefine these, also the border would break down. So now we will enable the fourth bit in the foreground color for these. So we will copy part of this up to here to write the attributes in the next byte, and the attribute will be the attribute, and then we will turn on the third bit, which we get by left shifting 1 by 3. So this will enable the next thing. And at the moment it just looks bright because of course it's color white. This is gray, and if you turn on the third bit or the fourth bit, if you start counting by 1, you will actually get color number 15, and that is a bright white. But it also signals to the VGA card to use a different character set. But the character set still looks the same because we didn't redefine it. All right. Then we also need to implement setting pixels and flipping the character set. First, flipping the character set for the double buffering, because that's actually relatively easy. We must only do this when we're in retrace. So we do wait for retrace. Then we'll swap the front page for the back page. So the pointers will get swapped. So now we're drawing into what was formerly the front page in the double buffering context. Then we will call the select maps routine, which I'll talk you through in a second. And our regular character set stays character set number 0. And if the current front page is equal to 0x4000. Then we'll pick character set 1 as our current front page, otherwise character set 2 in the VGA memory. And that's that. This will toggle after the swapping between 0x4000 and 0x8000, which are signified by the numbers 1 and 2 for the VGA card. And we will clear the back buffer so that we can draw again. So we take the character, we call it the character buffer, right? Character buff. Plus the back page offset. Otherwise we also clear the visible portion that we don't want to do. We're setting it to 0 bits. And we have to do hexadecimal 2000 to clear everything in that page. Okay, this should actually give us a clear screen, exactly. Now it's swapping back and forth already and drawing nothing yet, but it cleared out the second font. It's still white, but you can see it because all the pixels are clear. Good, we are almost there. Now we need to figure out how to set a pixel, okay? And then we will set 1 pixel, and after that we'll enable the cube. Setting a pixel. Well, it's a bit trickier than normal. We need to calculate the character number and the row number in the character. We also are gonna pick up a far pointer for the character itself, so we don't have to handle so many weird formulas around. We'll store the pointer actually there. We'll do a sanity check. If x is smaller than 0 or x is greater than the buffer width that we have allocated, and we need to left shift this by 3 or multiply it by 8. Or if the y-coordinate is too small or the y-coordinate is too large, buffer height times 16, then we return, because then we're out of bounds. Nobody can see the pixel. Now we calculate the number of the character in the map that we're gonna draw in according to our frame buffer layout. That is actually x divided by 8 plus y divided by 16, because this gives us the number of the character, because every character is 8 bits wide and 16 bits high, or pixels, so to speak, times the buffer width of our frame buffer that we allocated on the screen. And of course, for performance reasons, we will write this as a right shift by 3 and this as a right shift by 4. And this should give us the character number. The row number is actually also pretty straightforward, but the rows are counting up from the bottom of the screen to the top. So the bottommost is row 0 and the topmost is row 16. So we have to subtract from 16 to get the right row number minus the y-coordinate modulo 16, and then we will be off by 1, so we have to subtract 1 more. Then we can calculate the pointer in memory, which is our character buffer plus the character number that we just calculated times whatever height all the characters have, which is 32 lines. Even though we're only displaying 16, the VGA card always takes into account 32 lines in memory, plus the row number, plus the offset for our back page, because that's where we're drawing. Otherwise we're drawing into the front buffer, which we don't want to do. And if our on byte here is true, we want to send the bit, so we are taking the character pointer and doing an OR on that with a 1, and we left shift this by character width. This is the same basically as this computation, the row number. Basically we're calculating now the column number. We could also call this column number. Actually, maybe we should. Let's call this column and also calculate this. Column is equal to the character width, which should be 8, I think, minus 1 minus x modulo the character width. Great. 3 closing braces should do it. So here we're doing 1 left shift by column. Okay, this should shift our 1 to the correct position in the character. And if we want to clear something, it's very similar. But then, of course, we can't OR this, but we have to AND this with the negation of exactly what we just did, because this will set everything but that pixel. Okay, whew, quite a lot of stuff. Let's try to do a set pixel at 10. Now let's first do 0, 0, 1 for on. That should set something. This is wrong. There's too many closing braces, right? And here, yeah, of course, I wrote garbage. And there we go. And we don't see anything. Brilliant. Quick debugging time. Okay, very simple bug. I had to move the set pixel, of course, inside the loop, otherwise it would get deleted straight away. But this here, this pixel, that's us drawing something. And we can perhaps do t modulo, what size do we have? I don't know. Let's say 64 and t modulo 64. It will quickly draw a diagonal line. It should draw a diagonal line if we do t++. There you go. Or it traces out. It's even an animation, right? So we can draw at any space inside here. We can even do something like 256 and 256 and get it moving all the way up here before disappearing and then reappearing here. So awesome. Yeah, great. Which means we can enable the draw cube routine, because that's already done. We already did that in the previous video. Let's quickly talk about the select maps. I did this by using a register, not a direct register write, but an interrupt, because we have an interrupt for that. And it is part of interrupt 10 and sub function 11, which are the character generated routines. And here we're using the function 3 of this sub function, which is set displayed definition table. And you have to pass it the value for the character map select register. The character map select register is part of the sequencer. It's index 3 character map select register. And for the EGA cards, you have 2 bits to select character set A and 2 for character set B. And that's what we're doing here. We're basically taking whatever here map 0 has and limiting it to the lower 2 bits and the second map as well, but left shifting by 2 and then adding this. You could also have used an OR here. And this will give us exactly those 2 values. And these are actually the 2 additional bits for the VGA card, but we're ignoring that here and then passing it there. So we could have also done an output command on this register. So you might want to try with doing that as well. But nevertheless, enough talking. We have set up the screen, we are opening the fonts, we are drawing the cube and flipping the char set. So that should give us a rotating cube in bright white. And isn't that neat? There is a flicker here, which is not due to the double buffering or the text mode, but a bug in my fixed maths, I think. So every other frame gets dropped. If you hit the pause key, it will really disappear. Yeah, but I don't care right now. We have a rotating cube. That's very nice. But if you remember, these are actually all the characters from 0 to 240. And nobody's stopping us to put them somewhere else on the screen as well. Because we're only updating the bit plane containing the font. We still can put this somewhere else on the screen. And that's where this for loop comes in. It will copy the setup 5 times in different colors. So we can just enable that and get 5 rotating cubes for the price of 1, because the screen is actually drawn only once upon setup. And then we only ever update bit plane number 2 with the graphics data. And we only need to do it once to get 5 copies, even with this nice layering on top of each other, basically because we just obscured the invisible parts. But the drawing commands don't mind because it's in a different bit plane anyway, and the whole screen gets assembled by the VGA card on the fly. Isn't that great? That's something that you can't do in graphics mode. In graphics mode, you would have had to draw this 5 times. Your graphics code would get 5 times slower. But in text mode, you get this functionality for free from the graphics card, because basically it's a very simple tile-based graphics engine, similar to what you have on consoles, on like 8-bit consoles or 16-bit consoles, Master System, Mega Drive, NES or something like that, but very limited because you only get 8 foreground and background colors per 8x16 cell, or depending on what size you make your font, because you can of course do 8x32 or you can do smaller 8x8, but then you also only have 256 tiles obviously. But with these tiles you can do quite a lot of things, and I think this is quite a neat example of things that you can squeeze out of the VGA card that you can't do in graphics mode. So I hope you enjoyed this. This trick was not used super often. Sometimes it was used to create graphical mouse pointers like the one you're seeing on the screen here, but in text mode. Otherwise, people would just invert the attribute that the mouse cursor is currently over. But with this, you could manipulate the 4 overlapping text characters so that you draw a mouse cursor inside of it. But other than that, there was very little usage of this fancy trick that the VGA and also the EGA card could do. And I hope this was not too long. It was a bit longer because it's a bit more involved. The most important thing was understanding how the bit planes work, that they are only accessible in the graphics segment actually, and we had to reprogram the sequencer and the graphics controller to disable the whole odd even thing in text mode, but still keep the VGA card in text mode halfway, but also to enable access to bit plane 2 and then do the reverse and enable the odd even and all the other stuff when closing this thing. And of course, setting the pixel is a bit tricky because you need to calculate in which character you have to write. But once you have that, the sky's the limit. You can do almost everything that you can do in monochrome graphics. You can do a little bit of color, of course, but only on an 8x16 grid. Yeah, so that's it. Thank you very much for watching. Please share, like and subscribe. Put in your comments. Maybe you have other nice text mode hacks that you know about. Please share them. And yeah, you can also find me on Mastodon, chaos.social/@root42 if you want to connect with me. And Ko-Fi and Patreon is also available. And on Patreon I usually post this stuff a bit earlier. But that's it. Thank you very much and see you in the next video.